Okay, ready for another great day of formal methods? Now, I anticipated that there were going to be some questions about the homework that's due today. So I went ahead and took the liberty, before we got started, to put exercise 8.1, some information from exercise 8.1 up on the board here, because this one usually causes some questions. All right? So am I right?
Yes.
Okay. So I think it might be helpful for us to do the first, this is, you know, there's like, I don't know, 4 or 5 parts. There's several parts to this problem. So I thought maybe what we could do would be, I'll show you how to, I'll do part A for you. So if you just copy this down, you get free points.
It's A.U, not A.
Oh, it's A.U. Ooh, good call. All right. Now, this problem is to make sure, it's an exercise to reinforce the idea of a function having a type and how we notate that function having that type. So let's, what the problem gives us is it says function A has this type, function B has this type, C, D. I guess this is E, huh? And function E has this type. Now, do you remember what this cross arrow thing means? The problem is telling us that D has the type A cross C arrow D. Now, what does that mean for this function D? It has how many parameters?
2.
It has 2 parameters because 1, 2, right? And furthermore, this parameter has to have type what? A, and this parameter has to have type C. And so this is a function with 2 parameters, and it has, the first one has type A, the second one has type C, and it returns a value of type D. Okay, so the capital letters here represent types. You know, like Z, you know how we had integers, Z, and natural numbers, whatever. Okay, reals. Okay, so that's what these capital letters, and the lowercase letters are the functions, right? So what we have is we have these functions, A, B, C, D, E. In addition, the problem is telling us that we have a set of variables. And remember how we annotate variables. This colon is how we annotate variables. So this is variable U has type A, variable W has type B, variable X has type C, variable Y has type D, variable Z has type E, right? So we have a set of functions and we have a set of variables. And these functions have these types and these variables have these types. And what you need to say, what the problem is asking, it's asking, is this a correct way to call the C function? That's what the question is asking. For part A of the question, it's asking, is this a correct way to write down function C? Oh, I'm sorry, it's E. Yeah, my eyes, yeah. You know, the print, the older you get, the smaller the print. You know, this book, it actually shrinks. And the older I get, the smaller, the book is actually getting smaller. I can tell. Oops, whoa. And the lights are going off. Well, I'm really getting, my eyes are going, my ears. What's that you say? Okay, so this is function E. Okay, so how do you tell whether this is correct or not? The question is this correct or is it not? That's for each one of these, either it is correct or it's not correct. So here's how you tell. The way you tell is this. Well, can you tell me how you tell? What is the type of function E? How many variables does E have? It has 2. We know it has 2 here. Are you with me? No. And so in order for this to be correct, first of all, we have to count. 1, 2. 1, 2. The count's correct. So far, so good. Are you with me? Okay, so if the count doesn't match up, doesn't matter anything else. Boom, it's not correct. Okay, so two parameters here, 2 here. So far, so good. Now what we have to do is once the count is correct, you have to check and you have to see if these types are correct. Are you with me? No. Now, so here's the thing. What is the type of this? Whoa! What is A? Is it a function or a variable? It's a function. Okay, so here we come up as an A has a function. Now, how many parameters, according to this specification for A, how many parameters? Uno is right. It has 1. And how many parameters does this A have? 1. So far, so good. Yeah? Are you with me? So far, so good. All right. But now the question is, what is the type of this? Well, we have to check the type of U for A. Now, what is the type of U? Type of U is big A, right? So does this variable in A, does this first parameter have type big A?
All valid. Yes.
Well, hold on. Well, hold on. Okay, so this A takes type U. So what is the type of U? The type of U is big A, and this function A takes a variable of type, takes a parameter of type big A, and U is big A. So that's good, all right? And furthermore, what does this A function return? It returns a variable of type what? B. Well, does E take big B as its first one?
Yep.
Yeah, it does. So far, so good.
Type correct.
And what about W? W is a variable of type what? B. So sure enough, we have B, B. So this is correct. So this is type correct. Well, we used the cross thing when we looked at E. E had 2, right? 1, 2. 1, 2. A has 1, all right? So the 1 was, this is A dot U. So this is A of U. So U has type big A, and sure enough, function A takes A. So this one's correct. So what you have to do is you have to go through each one of those, and you have to examine. And the first thing you always check is how many parameters. If the numbers don't match, if nice bank shot. Okay, so is everybody does that answer how to do these? And you might have, some of these have like functions inside of functions. So if they do that, you got to start with the inside one and work your way out.
So what you do is you do like E of B, comma B, and then you can turn it into B cross B.
Now each one of these has to return a type of whatever the parameter has to be for that function.
And then the function could like return E or whatever if we went that far.
Yeah, we didn't. It was irrelevant for this question, but the function type E returns big E. So if this whole thing were inside of a parameter of another function, then we would have to use that. We would have to see if that parameter has type big E. I mean, requires type big E. Now, this kind of exercise is really a computer science exercise, because this is what you do. How many times have you written a program and it says type conflict, or something you can't do type, So, okay, is everybody see how? Are there any questions about this? About how this works and why this one is correct? Got it? Got it? Okay, now, other questions about the homework?
Questions about that?
Questions about this? Okay, let's take a look at this. This is our old knights and knaves. What did you have a problem getting it set up or solving or?
It's more solving, or I don't know, because I could have set it up wrong. That's why I can't solve it. But
Well, remember, the key thing is it's equivals. If
so, like for the first
so like for the first one, you say someone asks B, "Are you a knight?" He replies, "If I am a knight, I'll eat my hat." Well, there's just one Boolean expression that you write down. When he says something, Who said it? Yeah, so big B said it. So it's little b equivales, right?
Little b
Equivales what?
implies,
Little b implies top or h.
what do you want to call it?
Yeah, H. So equivales, B implies, yeah.
So then how do you solve for it? Because you have two, so you have to solve one to be, you have to solve one.
Well, you just have to manipulate. What I recommend you do is use one of those. I give you a hint. You have here an equivales and an implies, right? I would use one of those implies axioms or theorems to get rid of the implies and to get it with something that's useful with an equivales. Are you with me? Look, huh?
Do you mean like the 3.59 ones?
Yeah, those, yeah, up around there, up in that region, up around the our old friend 3.59.
Do you use implies for those? Like,
See, let me see, that like,
I use 360 and then strengthening.
I wouldn't use strengthening. I would use one of these.
I use 360 and then strengthening.
But I don't think strengthening enters in here. I think you can get that statement to equivale something that'll give you some information.
You have P and you have P implies Q. So that's B equals
Oh, I see.
H. And then you have just B, and then you just have B and H, and then you can.
Well, once you get, if you can ever get it to something and something, then you've got, this one and you also know this one. Well, look, if you ever get anything to A and B, then you know this. Then you know this is true and you know this is true.
All right.
If you ever get it into something, if you ever get into A and not B, then you know it's this, and you know A is true and you know B is false.
How do you prove that?
No, if you can get what that says down to this, then you know A is true and you know B is true.
So you just
so-
state that?
Yeah, I mean you're done when you get it to this because you know this and you know this.
So was it like
If you get it to this, not A and not B, then you know A is false and you know B is false.
oh,
Oh, okay. I got it down to that point.
Yeah, well then you're done. Yeah. No, well then you know because as long as what he said, as long as you can get it. Yeah, but you don't know what you're going to get. The thing of it is, we're not trying to get this to a theorem. I mean, we're not proving a theorem. We're just manipulating to try to get it to something that we can.
since we're just proving that you just have, is it all right to just say strengthening implies B?
You keep using strength. I don't think weakening, strengthening.
Don't you not need to use it because it just gives you B and H?
Yeah.
Yeah, you don't need. Oh, I see what you're saying. Because this. Oh, yeah. What? Yeah. No. I take it back. Yeah, you are right. If you get it to like A and B, you can say that implies A. So then you've done A. Yeah. Well, that's what I was saying. Yeah.
That's what I did.
Yeah. Or you can just get it to this, and you say, well, you know A and you know B.
Okay.
Yeah. I see what you're saying.
That nice.
Yeah. Your point was well taken. Yeah. And in fact, strengthening. It wouldn't be weakening. It'd be strengthening. If you ever get it to an or, like if you ever get it to A or B, you don't know diddly.
I mean, you could know it follows from A.
Well, I know, but you don't know diddly. You don't know whether A is true or false. You don't know whether B is true or false. All right. This is much weaker. This is too weak. Yeah. Are you? Yeah. This is too. I mean, you don't know diddly about either one of them, right? Are you with me?
Assume the disjuncts.
Yeah. There's no fair. We don't have a proof technique assuming the disjuncts of the antecedents. No, not ever. Okay. Now, does that help? Are you with? Okay. So yeah. And what's tricky about these word problems is you don't know what you're trying to get it to because you don't know what's true or false. So you just got to try to manipulate to get rid of to get it in a bunch of conjuncts, and hopefully it'll if it's possible to deduce what is actually the case, you should be able to do it by using these theorems and axioms from propositional calculus. I mean, predicate calculus. Yeah? So are we good? Does that help with that one?
Yeah.
Okay, good deal. Now, let me
All my breakfast sandwiches.
Ashley, can I see the book with us?
bring up the next. So let's see where we were here. We did these, right? We did these. We said we did this. Oh, we were talking about bound and free. Okay.
Oh no.
All right. Okay, so basically this 8.9 in the book is telling us, is defining what it means to be bound and free. Okay? Now, and what this statement says, suppose an occurrence of I in expression E is free, then the same occurrence of I is free in parentheses E, in function application, and in these quantified expressions. Now, here's what, here is an example of what that, of that. Suppose we have plus I, 0 less than or equal to I, less than or equal to 10, x to the I. All right? Suppose we have something like this. And it says, provided, oh, so here's the question. Is I in the list of dummies, yes or no?
Yeah.
It is. So is this I bound or free?
Bound.
It's bound. Is this x
Free.
in the list of dummies?
No.
No. Therefore, x is free. Are you with me?
Totally.
So does everybody understand bound and free?
See.
Okay. And this is defining free. Oh, actually, I introduced this in the concept of occurs. Let me give a couple of examples of occurs. We define occurs v, comma, e, in quotes, in single quotes, to mean that at least one variable in list V of variables occurs free in at least one expression in expression list E. So, and we actually did this, you might not remember this, but in anticipation of this, in an earlier lecture, we actually did this. So let's do some examples. Of occurs. Check this out. Occurs y in this expression, y squared plus 2y plus 1. So is it true that y occurs, that this variable occurs in this expression? Yeah, so this is true. Yeah? Here's another one. Occurs x in even dot x, in quotes. Is this true?
No.
Does x not occur in this expression?
Isn't that expression return type?
No. It doesn't matter what it doesn't matter what type it returns anything. Does this variable occur in this expression?
Yes.
Yeah, it does. So this is also true. Are you with me? Okay, and how about this? Occurs y. Now what we're going to have is we're going to have two expressions. Suppose we have x plus 24, comma, 2 to the y. Quote. So single quote y, comma, single quote x plus 24, comma, 2 to the y, end single quote. Is this true or false? Well, y doesn't occur here, but it occurs in one of them, right? So this is true. So does everybody understand how occurs works? Okay. Are we good? Okay. Oh, by the way, little quiz time from last time. What is this compartment called? The what?
Dummy.
The dummy. What is this one called?
Range.
The range. And what is this one called?
The dummy is also called the bound.
Yeah, it's also called the bound variable. Okay. And this was the range. And what was this?
Body.
The body.
Body of the quantification.
Body of the quantification. So dummy, range. And what is the type of the range? Always. Always what is the type of the range?
Boolean.
Boolean expression. And what is the type of the whole thing? The type of the whole thing is what?
Type of the xi.
Is the type of the body. Are you with me? The type of the whole thing is the type of the body. Remember that? No. Well, you remember it now. Okay. So now 8.10 is the definition of bound. Let an occurrence of I be free in an expression E. That occurrence of I is bound to dummy I in the expression dummy X, range E, body F, or dummy X, range F, body E, if I is one of the dummies in list X. Okay, so now let me ask you a question. X to the I, this expression, in this expression up here, is I bound or free? No. In this expression up here by itself, is I bound or free? It's free. Are you with me? So does everybody see that I is free in this expression? But in this expression, because I is free here, are you with me? Because I is free here, then when we put it in here and I is in the dummy, that makes this I bound. So if it's free here, but we put it in here and it's in here, then it's bound.
Is that what that's saying?
Hmm?
Is that what that is?
That's what that is saying. Well, it's a definition. I mean, it's neither common. I mean, you know, it's a definition. No. Definitions, you don't prove definitions. Definitions are like axioms. They are axioms. Yeah. So this is the definition of what it means to be bound. But now let me ask you this. Check this out. Now let me ask you this. Here what we have is times I, 0 less than or equal to I less than 4, body 5 plus I. Are you with me? Are you with me?
No.
You are. You're with me. Right? Okay? So now, in this whole expression, is this I bound or free?
Bound.
It's bound. Now what if we were to erase this and put this whole thing here?
Bound.
What if we double bound? Look, what if we were to take this plus I, 0 less than or equal to I, less than or equal to 10, and put this in here, times I, 0 less than or equal to I, less than 4. Yeah, good question. 5 plus I. Does everybody see what we're saying? What if we were to take this and put it in here?
Is it to the eye still?
Yeah, this eye and this eye are bound to what? To this eye, right? So this eye and this eye are still bound to this eye. So this eye is not free in this expression. Are you with me? This eye is not free in this expression. Therefore, this eye is not what? Bound to this eye.
Not bound?
It is not bound to this eye.
Yeah.
It is bound to
Are you with me?
Bound.
It's bound, but it's not bound to this eye.
So that eye
That's what.
that first eye has nothing bound to it. Well, besides the
Wait. This eye and this eye are bound to this eye, right? But this eye and this eye are not bound to this eye because they are not free in this expression. They have to be free. See, this eye is free in this expression. X to the eye. You see what it's saying? This eye is free. This eye is free in this expression. Therefore, this eye is bound to this eye. That's what that is saying.
you're just making it more confusing.
Well, I know it sounds a little confusing, but to be mathematically precise, this is how it has to be. This is how it has to be. Because we had the strict definition of what it means to be bound and free.
Alright, can we simplify that and solve it out?
No, I don't want to solve it out. I don't want to solve it out. That would not give us very much insight.
give us pleasure though.
But anyway, that's what that is telling us. Now, so which brings us to this next concept. Well, watch this. Okay, this one we will work out. Let's work this one out. Let's do this. Let's do plus I. Oh, we'll annotate this with the type. So we'll quantify over I, and let's just note that I is an integer. Yeah, it looks like a swan. 1 less than or equal to I less than 5, body I times x. So what does this mean? Or let's expand it. Ben, what do you think? If we expand this out, what will it be?
It'll be 1 times x plus 2 times x plus 3 times x plus 4 times x.
1 times x plus 2 times x plus 3 times x plus 4 times x is right. Are you with me? So far, so good, yeah? Okay, and what about this expanded? Plus j type z, 1 less than or equal to j less than 5, j times x. So, Josh, if you expand this out, what is it?
X times parentheses 1 plus 2
What?
plus 3.
No. Hold on, no. J.
Come on, keep up.
No, don't. We're not factoring. Come on.
1 times x plus 2 times x plus 3 times x plus 4 times x.
And what do you notice about these? What do you notice about these?
They're the same thing.
They are the same. Are you with me? This is the same as this. Okay? So that big insight here. These are the same. Now, what does that tell you? That tells you that if you have an expression with a dummy variable and you take every variable that is bound to that dummy variable here, you can just change the letter. And that does not change the expression. Okay? That means the same thing. All right? So what happens then is so what about this? So what about this? If we say plus, so plus I bodies Z, plus I type Z, range 1 less than or equal to I less than 5, I times X equals plus J type Z, range 1 less than or equal to I less than 5. Body J, right. No. Well, yeah. J
J times X.
J times
J times X. This now, but look, can we change the X to a Y? We can change all these I's to J's, but can we change this X to a Y? Can we change this X to a Y? Could we just put Y here?
No.
We could not. Okay, because this one is bound, this one is free. Okay, so
you cannot change the free ones.
you cannot change the free ones, but you can change the bound ones, and you have to change them all at the same time.
Paradox.
Yeah, the ones that are bound to the variable can change.
Right.
So if they're free, you can't do anything.
Right. So you cannot change this one because it's free, because it appears in the result. You see? And actually, you see, when you expand these out, the dummies never appear when you expand them out. It's only the free ones that appear when you expand it out. Okay? So cannot change this one. All right. So, who is next?
Also, a non-empty range is always bounded.
What?
Non-empty range is always bounded.
Well, it would be possible to have a range here that doesn't have a variable that's in here. I mean, it's
I guess, it's pointless.
yeah, but it's mathematically possible. Okay, so let's take a look at this. Let me see who is next. Okay, Rochelle, it's your turn. Now let's go through. So here's a big, complicated expression, right? And let's take a look at each one of these variables, and let's see if you can tell us whether it's bound or free. So let's take a look at this first I on the very left-hand side. This I, is that I bound or free?
Free.
That's free. Okay. Ashley, what about this J, bound or free?
Free.
Free. And what about this 1 less than or equal to I less than or equal to 10? Mason, bound or free?
Bound.
Bound to this I. And what about this I in B sub I, Ben? Is that bound or free? Bound. And what about this J, Josh, bound or free? Free. And what about this I, bound or free? What about this I, bound or free? Bound. And what about this J in 1 less than or equal to J less than 10? Ashley, what do you think?
Oh, sorry.
This J,
Bound.
bound. What about this I, Mason?
I would say it is bound
It is bound to what?
to that I.
To this sigma I. Yeah, to this I over here. This I is bound to this I
Because it's not bound to anything.
because it's free in the expression by itself, but it's bound to the I.
Yeah, because you'd solve like that expression first, right? Like if you did everything out, like you solve that expression and then you'd have to solve.
Then you would do that one, and then there would be no more I's in and there would be no more I's.
Yeah.
Okay, so Josh, are you with us here? This I is free in the sigma j quantification.
Yeah, I have that.
But that sigma j is in the body of a quantification over I. So therefore, this I is bound to this I.
Say there was a J next to the. Say it was sigma.
Good question.
Say it was sigma I comma J
No, yeah,
over there. Then would the other J just be bound to the first
Yes,
j and not the other one?
correct. Which is what we did over here with the I, remember?
Are we solving that out?
No, we're just identifying bound and free
How
variables.
would you do that?
The idea would be like I.
Well, here, okay, you could solve, we could in our minds solve it out.
Like the-
First, you'd have to do the inside one. The inside one, what are the values of j? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right?
Yeah.
So then what would happen is, this would be c sub i1 plus c sub i2 plus c sub i3 plus c sub i4 plus c sub i5 plus c sub i6 plus c sub i7 plus c sub i8 plus c sub i10,
Alright,
right? And you'd have that whole long thing.
okay.
And then for each one of those i's, it would be that one with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
So
The next one, 1, 2, 3, 4, 5, 6, 7, 8, there'd be 100.
Yeah,
There'd be 100 terms.
let's not solve
Okay,
that.
so you'd have to rewrite all of the C, I.
You would first write out this one, this center one, and that would have 10. And each one of those would have an I in it. But it wouldn't have any J's,
Right.
right?
Would program a calculator do this?
Sure, that's easy. A nested for loop, you're adding up 100, it's a 10 by 10 array, and you're adding up 100 elements in an array, in a 10 by 10 array.
And then you'd add on to that all of this.
And then you would add whatever this turned out to be. Yeah. But the point here is that this I is bound to this I. And this J is bound to this J. Now, are we clear on this? Are we good?
So all the I's would go away.
Well, except that all the I's in here would go away, and all the I's in here would go away. But this I would stay, because this I is free. Does everybody understand that this I is not this I? This I outside is not the same I as this I. In fact, it's a little confusing. If you ever have a situation where you have something like this, you know, if you have something like this, if you have like J, or here, let me do, now let's say, suppose you have J times the sum on J, I don't know, 0 less than or equal to J less than 5, body J times X. This is a little confusing because this J has nothing to do with this J. So in order to keep it from being confusing, it would be better to rewrite it like this. You would have to keep the J, but then have this be sum on I, 0 less than or equal to I less than 5, I times X. Okay? This is called dummy renaming.
What, just so you don't confuse.
Just so, yeah, this is a little confusing. These are the same thing, but you have a J here, you have a J here. You know that this J is not this J. So it'd be less confusing to write it like this, because that, you know, just, both of these are mathematically correct and equal to the same thing. But, you know. So that's called dummy renaming. All right. Now, the next thing we need to know is how to do textual substitution. All right? Well, because we're going to do textual substitution, what happens if you have a big thing like this and you want to do textual substitution in it? Now, what's our rule for textual substitution? When you do textual substitution into something like this, you know, if you want to do textual substitution into this, what did we know about I? This I is what? It's bound to this. And the final result doesn't depend on this I, right? Yeah, so you can rename it. You can rename it. But how do you do textual substitution? The only way you can do textual substitution is if what? Provided what? What does it say there? In 8.11, it says provided not occurs Y in what? X or F. And what does it say? If you're going to do textual substitution and the dummy variable is Y, you cannot do it if that Y occurs in either X or F. And so if it does occur in X and F, you have to do dummy renaming first. Are you with me?
R.
Are you with me? Okay? So you can do dummy renaming. The way you do, what this says is that the way you do dummy renaming is you do dummy renaming in the range and you do dummy renaming in the body. Sorry. Cross that out. Maybe we can bleep that one out. So the way you do textual substitution is you do textual substitution in the range and you do textual substitution in the body.
And you don't do it in the dummy.
And you don't do it in the dummy. And furthermore, not only do you don't do it in the dummy, but you can't do it. Because this only works provided y is not in x or f. So if y is in x or f, what do you have to do first? You have to rename the dummy. Then you can do the textual substitution. All right, so with this in mind, well, with this in mind, let's see if you can figure out what these textual substitutions are. The first one says plus x, range 1 less than or equal to x less than 2, body y. All right? And it says y replace y plus 2, textual substitution. Now, how are we going to do this textual substitution? Well, first of all, we have to check our occurs, right? Now, does this x occur anywhere here? Does it? Yes or no? Does it occur? Does this x occur anywhere in what we're going to do textual? So as long as the dummy doesn't occur there, you textual substitute the what? The range and the body. So what happens if you textual substitute the range? What do we have?
Nothing.
Yeah, it's 1 less than or equal to x less than or equal to 2 still, right? And what happens if you do textual substitution into y? What do we have? Y plus z. So therefore, what is this? It's plus x what? Range 1 less than x less than or equal to 2. Body what? Y plus z. See if we got it right. Are we good? Is everybody clear on this? Okay. Now here, next one, sum over I. We're going to quantify plus over I. And what is it? 0 less than or equal to I less than n, body, b sub I equals n. Okay. Now, what do we have to check? Is this I in here? N replaced by m. Is that I in there? No. So we just do it. Okay. So Ashley, what is it?
Plus
I.
0 less
than or equal to I.
less than n. I mean,
0 less than or equal to I less than
m.
m.
Body.
Body
B. I don't know how you say it.
b sub
D sub I equals
equals what?
n.
M. Yes. Okay. So 0 less than or equal to I less than m, b sub I equals m. Okay, Mason, you get the tricky one. What do we have here? This is plus over y, 0 less than or equal to I less than n, b sub y equals n. But now what are we doing? N replaced by what? Y. Well, holy moly. What about our occurs? Unfortunately, y occurs in here. So what do we have to do first? So therefore, what do we have to do first? Yeah, we have to rename the dummy. Because we can rename the dummy. That means the same thing. So pick a letter. What do you want? What letter do you want? So we have to rewrite this. So what's it going to be? Plus, pick a letter that's not, no, you got to pick a letter that's not in here, right? Okay, so pick a letter. Q? All right. Q, sum on Q, what is it? 0 what?
0
Less than or equal to what?
to
Q. Yeah, we're in it. Okay, less than what? Less than what?
Less than y.
No.
Oh.
Less than, we're just dummy renaming. We're not textual substitution. We're just
Less than n.
less than n,
And then
a body, what?
b sub q
B sub q
equals n
equals n.
with n replaced by
And now this whole thing, and now we're going to do n replaced by what?
y.
N replaced by y. Right? So we have to do that first. Okay, and now what do we do? So now what happens? If we do this textual substitution in here, what do we get?
Plus
plus Q, 0 less than or equal to Q, less than what?
than Y.
Y, okay, so this one's going to be Y
Can't see it.
So this one's going to be Y, and then what? B sub what?
Y. No, B sub Q
Oh, yeah, it's B sub Q
equals Y.
equals Y. Yeah, so that's what that will be. So let's see if we got that one right. Now, of course, the Q, they probably picked a different letter. Picked J. But are you with me?
I have a question. What if N occurs in the dummy? Then
You cannot.
you cannot.
You cannot. No. Yeah, if it's a dummy, then you can't do it. Okay? And what about, Ben, what about this one? What about plus Y, 0 less than or equal to Y, less than N, B sub Y equals N? This is Y replaced by M.
Then it would be,
What do you have to do first?
well, first you have to replace the y with m.
No. This Y occurs here. So what do you have to do?
In the range and in the,
Well, what do you have to do with this whole thing?
you have to,
You have to rename the dummy,
yeah,
right? So if you rename the dummy, so you have to pick another letter.
I can't use any of the ones there.
No, you have to pick, yeah.
Pick m.
M is here. You can't pick
You
that.
can't do it.
Oh.
You can't do it.
You have to pick another letter. There's 26 letters in the alphabet.
Pick A.
A, okay, so this would be plus what? Plus A,
Use that.
range what? Range what?
0 to
Less than or equal to A,
You can use N because it's.
less than
and less than
N, body what?
the m.
A.
A,
Oh, yeah,
B, A
equals that.
equals N, and now we're going to do textual substitution what?
Y replaced by N.
Y replaced by M.
That doesn't do anything.
Well, but we know from how textual substitution works that if it isn't here, then we're just left with this.
Yep. So if.
All right. So when you do this textual substitution, this equals by textual substitution the same thing. Plus A, 0 less than or equal to A, less than N. B sub A equals N.
Oh, so that's what I was saying.
Are you with me? Base textual, so if it's not, right?
The Y called in the textual substitution like that. It's something.
Y replaced by this.
Yeah, well, I mean, what's the title, like, you know how that.
I don't, it doesn't have a name.
Doesn't have a
It, that's little, no, it doesn't. It's not like antecedent or consequent. Let's see how we got it. So yeah, they picked J instead of A, but it's the same thing, right?
Yeah.
Are we good?
So if the stuff to the left on the replaced by is in the dummy, then it doesn't do it.
Yeah, if what's in the left is not here, then,
Could you just drop the textual substitution?
well, yeah, you could dummy rename this back to the original one.
Yeah, so I mean, if we see that and we see that.
Well, yeah,
Y
you
is
could,
the
yeah,
dummy,
you
just
could.
drop it completely?
Yeah, you could. And then there's, before we go, so this is how we do Leibniz, okay, with this quantification. So basically, because what are the two things with our proof? How to do textual substitution and how to substitute equals for equals. And what does this say that you can do when you to substitute equals for equals? Same way as before. Okay? So you can basically what this says is that you can substitute equals for equals
As long
in
as X isn't in P and X isn't in Q, right?
No, we don't have any occurs here. There's no occurs.
But what if,
No, there's nothing with occurs. If we know that P equals Q in all states, we can do it.
but what if there's an X in,
No, there's no occurs proviso. There's none.
I like how we use P. It's like cookies.
Yeah, there's no proviso. This works. Okay. What it says is that if P equals Q, we'll see many examples of this as we get into it. But basically what it says is that if you know that P equals Q in all states, then you can substitute equals for equals in the range. Are you with me? So in this range, you know, wherever there's a P, you can make it Q in the range. It also says that you can do it in the body. This one says you can substitute equals for equals in the range. The second one says you can substitute equals for equals in the body. But in the body, it's even better in the body because P doesn't have to equal Q in all states. P only has to be Q in those states for which R is true. So you have a little bit more flexibility, but for all practical purposes, we'll never use this R implies property of substituting equals for equals. In practice, all the proofs that we have, if P equals Q in all states, then for sure R implies that. Okay? All right. And then next time we're actually going to start looking at the axioms and theorems for quantification. So we'll start in on our list. You know, we'll get back to your Bible of axioms and theorems. All right, good deal. See you next time.